Hello and welcome to the second installment of my Blender Python script video series. In this episode, I will be looking at a bevel2d script. A bevel is defined as a sloping surface or edge. I will not go into the details of that definition or the different types of bevel, chamfer, fillet, and so on. Suffice to say that the process of beveling in computer graphics is the rounding or smoothing of a corner where two or more edges meet. The bevel2d function works on two edges. Of course, Blender already has a built-in bevel modifier, which is sophisticated, versatile, and simple to use. So, to make things clear, the main point of this presentation is to provide an insight into the process. In my opinion, learning how things work at a base level improves our understanding of their application and utilization. Furthermore, you could use the bevel2d function to create line paths for object placement. I will talk about vectors, line paths, and object arrays in future episodes. Let me first point out that these episodes are not for complete beginners. If you have difficulty following along, there are many websites that help you with Blender Python scripting concepts. One highly recommended resource is the official Blender Python API documentation website. The Python modules for this presentation can be downloaded from my GitHub channel. The link is in the video description below. Download the zip archive and extract the files to a folder on your computer. Start Blender and save a new file with a name like bevel2d or anything you want. Delete any default objects in the file. Select a scripting workspace and open the demo modules in the text editor. The actual function is in the bevel2d module, and the code is fully commented. Looking at the function, we can clearly see the 5 distinct steps which correspond to the transformation matrices used. But I think it would be better to explain them visually. Suppose we have two perpendicular edges along the x and y axis, both starting at the origin, and we want to bevel that corner, which is a right angle. If we set the offset at say 1.5 units and then we draw parallel lines from those points, we have a square. Therefore the points P1 and P2 lie on the circle of center C and radius 1.5. We draw the arc that connects the 2 points, say we wanted 6 segments, and we have our bevel. Now that was easy enough. Next, consider a case where the angle between the two sides is smaller than 90 degrees. We still have the same offset, however, when we draw the parallel lines, the shape is not a square, but a parallelogram. So the bevel in this case cannot be an arc. Indeed, if we draw the arc between the 2 points, the resulting curve looks nothing like a smoothing of the original shape. We have to consider other cases as well, like when the angle between the two sides is bigger than 90 degrees, and what if it was 0 or 180 degrees? The problem now becomes complicated since we want the function to deal with all possible cases. So let's go back a bit and try to visualize the function steps. Let us also move the intersection point away from the origin because that is yet another case we need to consider. Okay. From the input parameters we have the 3 points A, B, C, and A is the intersection. We are also given the number of bevel segments and the offset distance from A. Note that when I say points, I am talking about location vectors. That is, the point coordinates represent a 3D location, but the type of the variable is Mathieu-Till's vector, which allows for vector math operations. First of all, we need to establish whether there is a solution to the problem. So we take the sides AB and AC and we make sure that they are not parallel or of zero length. We use the cross product of the two vectors to check that condition. If the test failed, we simply return a list with one element, the intersection point A. Then we get the three vectors P1, P2 and PC that we will use to calculate the coordinates of the bevel points. The idea is that we want to move these points such that PC is at the origin, and points P1 and P2 are the X and Y boundaries of the first quadrant in a unit circle. In step number 1, we make sure that our points are on the XY plane. Now, this is not possible to show in our little diagram animation because I'm using the top orthographic view, but it will become clear when we run the demo module. Essentially, what we do here is we first obtain the ABC plane normal vector Pn, which is the normalized cross product of AP and AC, and then we check the condition for parallel unit vectors with the XY plane normal. If the vectors are not parallel, we use a rotation matrix representing the rotation from the XY plane to the ABC plane, and we rotate the points P1, P2, PC by the inverse of that matrix. The term 1e minus 4 here is simply another notation of the literal 0.0001. You can check that out on the Python Interactive Console, which, by the way, is a great tool to run quick tests or to find information about Blender Python structures using the auto-completion feature by typing a few characters and then pressing the Tab key. In step 2, we move the points so that PC is at the origin, using the inverse of the translation matrix of PC. Note that we only need to apply the transform to the points P1 and P2. In step number 3, we want to align P1 with the x-axis. This involves a rotation matrix representing the rotation between the x-axis and vector P1. I obtained the rotation quaternion using the signed angle between the two vectors, but I could have used the vector to track quad method to the same effect. Remember that we must convert the quaternion to a 4x4 matrix and apply its inverse to both P1 and P2 vectors. In step number 4, we use the inverse of a shear transform matrix to align P2 with the y-axis. P1 is not affected by this transformation. Finally, in step 5, we store the scale of P1 and P2 in a diagonal or scale matrix. At this stage, we get the list of the bevel points on the arc in the first quadrant of the unit circle. Then we compile the transformation matrix. Remember that transforms are applied in reverse order, and we use that to adjust the final coordinates of the bevel points. And that is the complete function. Needless to say, there are many ways to write a bevel algorithm. This is a simple implementation which you can easily optimize and customize to suit your needs. I hope the summary was clear enough and the step sequence logic makes sense. For a demonstration, we turn to the B2D demo module. You will notice there is a requirement at the top, which means we need some objects to run this module. This is taken care of by the accompanying setup module. Select it and run it once to create the necessary objects. Now, select the B2D demo module again and run the script. The side panel is just a dummy. Click the demo button to activate the operator. Here you have the 3 points A, B and C, and the first one is marked anchor to indicate that it represents the intersection of the two lines. Then there are fields for the offset and segment values, and 3 checkboxes that allow you to control the display of the bevel points as objects, as a mesh, and whether you want to see the ABC plane normal. Change the coordinates of the 3 points and the values for offset and segments to see the effect. I hope you liked this episode. If you feel you've learned something, you might consider liking and subscribing to the channel. Thank you for watching.